Welcome to rigorous training in longitudinal data science. Radiance.
I'm going to be starting today's lecture that is on research methods for multi-level data. And in particular, in today's presentation, we will be looking at what we mean by cluster data, and also we will be introducing what we call random intercept models. So at the end of the whole course, you should be able to familiarize yourself with different types of multi-level data, and also understand what are the strategies that you should use to analyze this data based not only on technical but also substantive reasonings. And hopefully you're going to be able to actually also understand how the outputs that Stata give you should be interpreted, and also how to actually estimate those outputs. And we will do this random intercept and random slope models for both continuous and binary outcomes. Today, we will be starting with the concept of a multi-level data sets, and then we will see why we should use appropriate methods when we're dealing with these data sets. Then we will also introduce this idea of partitioning the variance, and therefore distinguishing between the so-called individual and cluster level variances. And having done that, we will then introduce the first model, that is the so-called random intercept model. And we will see how also results from these models are interpreted. In today's lesson, we will be doing example with continuous outcomes. And this is going to be the same also for session 2, whereas in session 3, we will introduce binary outcomes. So let's start with this first question, that is, what are multi-level data? So these are data that are structured in this way. So where you have individuals at level 1, in this case, for instance, pupils, who are nested and clustered in different level 2s, which in this case could be schools. And then in this example of multi-level data, we also have a third level of clustering, that is the area where people live, so the region or the local authority area. And when we have these data sets here, one can expect that maybe the students that go in a specific school might actually share certain characteristics, so they might be quite similar, because maybe they live in a certain area, or because pupils from certain backgrounds are more likely to go to certain schools than others. And at the same time, one can imagine that maybe also the school themselves, if they are in different areas, might also share characteristics that make these schools, for instance, more similar than schools 3 and 4. So when we have this structure of the data, we call this multi-level or hierarchical data sets. And this could be naturally occurring. So you might actually have, like we saw in the example before, you could actually have pupils to attend schools who are in different areas, who happen to be in different countries, and so forth. So there could be clustering happening at different levels. Sometimes also we might have cluster data that has been clustered by sample design. And this could be cases where people were drawn from different areas of the country, or from urban and rural areas, and then big and small cities and towns and so forth. And then the other case of multi-level data that is slightly different than the ones that we have mentioned so far is when you have the same person that is observed at different times. So in these cases, technically, the data is also clustered within the same individuals over time. But when we have repeated measurements, we usually call this data longitudinal data. And the interpretation of the results when we have longitudinal data is slightly different than it would be for multi-level data sets. And of course, there could also be a combination of all of the aboves, which could determine and make the data look multi-level. So when we have this structure of the data, why should we bother by introducing analysis that account for these different levels and clustering of the data? So technically, there are two reasons. So the first one is more of a technical reason why we should be accounting for the fact that the data are multi-level. But also, we might have research questions that are multi-level. And I'm going to give you, an example of both and also some reasoning as to why we should account for multi-level data, for sure for technical reasons, but also for substantial research questions. So we might have to use and account for multi-level analysis because the clustering creates some issues. So if you remember, or if you you might not remember, but if that's the case, then let's refreshen the assumption of a simple linear regression modeling. If you remember, one of the assumptions of linear regression modelings are that there has to be a linear relationship between the exposure and the outcome. Then we should include all the key covariates and make sure that we are accounting for potential covariates in the model. Then we also have to check usually the residuals of these models and make sure that these are normally distributed and they have ideally homoscedasticity, so constant variance. But one of the assumptions is that also these responses should be independent of each other. And as you can imagine, this is the assumption that doesn't hold when we have clustered data. And this is because, we might expect, for instance, that people who attend the same school, pupils who attend the same schools, or residents of a certain area might actually not be independent of each other in their responses. So if you're looking at the grades in maths, students who have the same teacher might have a similar trend and their respondents might not be independent of each other because they all were exposed to the same lectures by the same teacher. Or you could think of, for instance, life satisfaction in a certain country like the UK might be different than the life satisfaction observed in the US, for instance. So there might be country factor that shape that answer, and therefore, there could be the assumption of independence could not hold. But then we might be also interested in substantive research questions that actually are more related to the clustering than to the level one. So we might actually be interested in estimating the amount of variations that there is for instance, between countries, between schools, and so forth, but also to understand whether there are some explanatory variables at the second or third level that could explain the differences that we observe at level 1. So, for instance, we might be wondering whether the students' academic progress and marks vary between schools. So, if there is a lot of variations between schools, and therefore, we can then try to see which are the schools that do better, the schools that don't perform as bad. And as a policymaker, we might try to understand, what are the factors that could reduce that variability and lift the students in the poorer performing schools to higher levels of academic performance. Or we might ask ourselves, if the health outcomes actually vary across different regions in the country, and also understand, what are the factors that are driving that variation across the different countries. So, could it be, for instance, access to healthcare services? Could it be presence of hospitals and beds, so long-term care? So we could also try to understand not only if there are differences, but also which are the factors that could explain the observed differences across the areas. So these are, questions where we might not only have to account for research for the group and the level and the nested structure of the data, but we are also substantively interested in the level 2 or level 3 factors of these nested data sets that we have. So in theory, there are alternative strategies to multi-level models. So, one could ask you, could we just, look at other strategies, or, could we, for instance, just use fixed effects where we account for the countries that we have? Or maybe, if we have a design-based modeling, could we just, account for the survey settings? Or, for instance, could we just use a normal linear regression modeling where we adjust for the standard errors and we adjust for the fact that the data is clustered within different countries, for instance. So generally speaking, these are potential strategies, but increasingly, there is kind of a more and more evidence to suggest that this, when the data is indeed multi-level, we should be using the correct multi-level approaches, and this should really be the default approach. And this is quite important, especially for the estimation of the variation across the groups. And also, when we only have, for instance, country as an effect, we are in a way averaging everything, to one level. And we don't really take into account the fact that there could be quite substantial differences in the relationship as well as in the averages of the relationship between the outcome and the explanatory variable across the countries. So, that's why we have this course, and it's always quite useful and important when you have these data sets to have these approaches. Modeling. I just also want to remind you, and this is something that sometimes is quite confusing, that different disciplines and also over the years, the name that we use for multi-level modeling might be different. So multi-level models are also known as random effect models, mixed models. Oftentimes you can also hear me say hierarchical or nested models. They're also known as variance component models because as we will see that you can differentiate between within and between variance, and also as subject-specific models because these are not averages and they take potentially the subject or the countries into account. But no matter how it is called in your discipline, when the data is multi-level, most often and more recently, you would be reading and using models that actually account for this structure. And the name, as I said, could be slightly different depending on the disciplines and depending on the journals that you read in your area of research. So why is it important, and why should we account for the structure of the data? So let's assume that we have here about 16 observations with a certain continuous outcome and a certain exposure. If we don't account here for the structure of the data, it really looks like that there is no relationship at all between these two variables. So if you were to fit a straight line, this would be parallel to the exposure, suggesting that no correlation and no linear relationship between these two variables. However, if I told you, that this data came from 4 different kids observed in 4 different schools, all of a sudden, you could see here that there seems to be some kind of a relationship within each of the school that is labeled in a different color. So if we didn't account for the structure of the data, we would actually come up with this wrong conclusion. Whereas if we tell our statistical packaging programs that this data come from different schools or different countries, then it looks like that there is a positive relationship between the exposure and the outcome that we have observed among these subjects. So this is a very simple, but I think quite important visualization. The structure into account might actually lead to the incorrect conclusion, and why we shouldn't just use simple linear regression models or the standard ones. So then when we account for when we kind of need to take account for the structure, it's also important to remind ourselves what is the variance and how it's usually defined in regression modeling. So the variance is usually a measure that tells us the variation that we have of the data around the mean. So this is the kind of formal definition. So it's the average of the square differences from the mean. And it really tells us the mean, how different and how far away each of these dots are compared to the mean and the straight line. And variances, of course, can be as high or as small. Usually ranges between 0 and plus infinite. If the variance is equal to 0, of course, that means that every single subject is on the straight line. Whereas as the variance increases, and also as the standard deviation also increases, there is more the distance between these dots, and the mean straight line also tends to increase. So if we apply this concept of the variance to the kind of a simple or single level regression modeling, then let's assume that we have a regression modeling, in this case with an empty model, so where we don't have any x, so there is no any explanatory variable here, and we're just looking at the kind of a structure of the data and the data set. So we could have a simple case here with 3 people, where we have observed the outcome variable and the main variable of interest x. But for the time being, we're just interested in these observations of the outcome y1, y2, and y3. So if we don't have any x's in our standard regression modeling, then our regression model would be written as yi that is equal to a certain average plus or minus a residual. That tells us how far away that specific observation for subject I is from the is from the predicted average. So if we see it on a graph here, we would have the average observed across all of the three dots here and all of three data. And then the residuals would tell us how far away each of these observed y's is from the average beta 0. So this regression line would be the one that minimizes the distances between y, I, and the straight line. What happens when we have more, when we have correlated residuals and therefore subjects coming from different countries in this case? So let's assume that, that not only we have these observations, but now we are also introducing a level or a grouping of these observations. And we assume that some observations were from country Spain, and these other observations down here were from were observed in Germany. So in this case, the residuals within each of these clusters are likely to be correlated with each other. And effectively, we can therefore, if we have here a new notation that tells us that this is an observation for subject I in country J, so this could be, country 1 and 2 for Spain and Germany, respectively. And then we would have, for each of these people, a number for their observations. So in this case, we could calculate the distance between, let's assume that we are focusing on subject here 4 in country 1. So if we look at subject 4 in country 1, this is the value. Actually, let me see if I can actually add. There you go, a laser point. So let's assume that this is the observed value for a certain person. So subject number 4. That was observed in country number 1. So in this case, the distance and the error that we have between this observation and the average can actually be split into two parts. So the residuals here can be split into two bits of residuals. We would have, the cluster effect, that is the level to residuals, that is the distance between the average observed in the country Spain and the overall average. So this would be the country residuals or the level to residuals or the cluster effect. And then we would have an additional part that is the individual effects. And this tells you what is the distance for that specific subject in that specific country to the average that was observed in that country. So that's why when we have cluster data, we can split this distance for a specific subject into two components, and we can therefore calculate the so-called cluster effect and individual effects components with two different residuals, the country residuals and the individual level 1 residual. So we can now we can now partition the variance into two sources. So if you remember, in the simple model, we only had one residual element here, whereas when we have grouping, this bit here can be split into two sources of variances. So we can calculate, the between group variances as well as the within group variances. And both of them, we assume that are normally distributed with an average of 0 and a certain variance, like we do for the one level standard linear regression models. So what this means is that now, if we have different clustering, and of course this is an example where I am imagining that the clusters are quite separated from each other, and there is quite a neat separation between the various clusters. But effectively, now we can calculate how much variations there is between these clusters compared to the overall level. So I'm going to say it again. We can calculate how much variation there is here among all of these clusters compared to the overall level beta 0. So obviously, if all of these clusters were overlapping and they were overlapping with 0, there would be no variation across the groups. So it wouldn't matter if you are in Germany, in Italy, Spain, or the UK, the averages in all of these countries would be the same and equal to the overall average. Whereas the farther away these cluster-specific means are, the more variation there is across the groups and between the groups. And then the second part would be, the within cluster variation. So obviously, in this case, I think I've probably copied and pasted most of these values here. So, the variation within each of the countries seems to be quite similar. But you could also have cases where, maybe in one country, all of the dots are really close to one line. And in another country where there is more variation within that country and farther away distances of these dots compared to the country-specific straight line. So what this also means is that we can calculate what we call the variance partition coefficient. That tells us, and this is the case where we only have two levels, because it gets a little bit more complicated with more than two, but I think once you get the concept, this applies to different levels as well. But the idea here is that we can determine how much of the total variance is due to differences between groups. So if you remember, the total variance, that is the denominator of this fraction, is given by the sum of the of the between plus the within country or group variance. And in the numerator, we would actually have the variance observed between groups. This we usually refer to as the variance partition coefficient. It can also be known as the ICC, so the intra-class correlation coefficient. And as we will see in the practicals over the next few days, we will see both how this can be interpreted and also how this changes or can change once we introduce more predictors in the model. But technically, the variance partition coefficient is a ratio of two values, and it can only range between 0 and 1. So if it's equal to 0, it means that there is no group effect. So effectively, what it means is that the country-specific line or the country-specific average would be equal to the overall average. So if you were to calculate here the country-specific effect for circles and triangles, these two lines would coincide and would be also equal to the overall average observed in the whole sample. And if this was the case, this is a very extreme case, I have to say, but if this was the case, then we might not even consider multi-level models. So if we have a VPC or an ICC equal to 0, then that's the only time when you're allowed to use a simple linear regression model, or like by simple, I mean the standard that doesn't account for country level structure, because you will get exactly the same results. Whereas, in the other extreme event of VPC equal to 1, so when the variance partition coefficient is equal to 1, what it means is that effectively there is no within country individual variation. So although the two lines that we observed in group circle and group triangles are different, and within each of these groups, every individual has no additional distance compared to the overall average, which means that these data here are all lying on the straight line within that specific country. In all of the other cases, how do we interpret this ICC or VPC, and how do we estimate it? So this can be estimated in manually if you want it, because once you tell Stata, R, or any of the other packages that the data is hierarchical or multi-level, these packages will give you estimates of both of the variances of the residuals, as well as the variances of what is called here the constant, that is the variances at the group level. So you can then calculate it by summing and dividing these values, or you can just use a command in Stata, as we will see in the practical. And what this value here at 0.13 means is that about 13% of the variation that we observe in our outcome variable is attributable to differences between countries. So this is even without accounting for any covariates in the model. So here we're just saying that regardless of whether you're interested in BMI, or you're interested in life satisfaction, depression, or any other outcome variable, and no matter whether you're accounting for gender, age, socioeconomic status, and so forth, even without taking any of that information into account and just looking at the structure of the data, here this value suggests that about 13% of the total variation that we observe in the BMI values, for instance, or in life satisfaction values or depression or whatever your outcome variable is, is attributable to differences between countries. And given that this is not equal to 0, that suggests that we should take this structure into account when we are estimating and calculating and when we are analyzing these kinds of data. So this is what we call the null model. So this is a model where so far we haven't even considered any potential covariate or any potential variable of interest that we are, or any other relationship. So at the moment, I'm just telling you, this is the data that we have for a certain outcome, and we can check by looking at what we call the null model, how much of the residuals is attributable to country level differences or person level differences. So in this null model, even without accounting for any covariates, we can already see that there are two parts in the model that are the fixed and the random parts. And that is also why sometimes these models are known as random effect models. So you have here the overall mean that is fixed. And then we have the kind of a distance between that mean, let me put this back on. So we have here a fixed part, and then the distance between this fixed part and the specific observation Yij is equal to the sum of these two random parts that are the first one telling us the distance between a country specific. I'm gonna stick to country just so that we have a structure of our data in mind. So the distance between that country specific. So if this person here was observed in Italy, that would be the distance between the overall mean and the specific mean observed in Italy, plus or minus, of course, the specific individual distance for that subject within that country. So this is what we call the level 2, so group residual, and level 1 or individual residual. And as it happens also in the classic linear regression model, we assume that these two residuals are normally distributed with an average equal to 0. And then these two values here that are usually observed and estimated using our data. So what happens when we have mixed models or random effects models or hierarchical models is that this structure of the data and these two values can be accounted for and calculated. So what happens then when we also introduce a covariate? And in this case, we introduce the variable x. So in this case, and this is the focus of today's practical, we're going to be talking about random intercept models, because what we will do here is that we will have the slope for the variable x as fixed. So we will allow the intercept to change across the different countries, but the slope is going to be fixed and does not change across the various groups or country. So this is a random intercept only model, because beta 0 varies across countries, but the slope doesn't vary across the countries. And the way we interpret these values is the fixed part is really the same way that you would interpret a classical standard linear regression model. So this would really just tell us, the overall value of the outcome when x is equal to 0. Oops. And then the beta 1 coefficient would be the average slope for the relationship between x and y. So it would tell us, if this is a continuous variable, for instance, that as x increases by 1 unit, on average, y will change by a factor of beta 1. And then the random effect parts will tell us how much variation there is both within clusters as well as across the clusters. And by allowing the estimates of these random effects parts, we actually also deal with the issue of non-independence. So by allowing, this calculation and the fact that, that the slopes are different in each of the countries, and therefore that each of the country might have slightly different, that these countries are, that people within those countries are not independent, we also resolve the issues of independence at the country level, so at the level 2. So effectively, what happens when we calculate random intercept models is that we only obtain these two values here, beta 0, beta 1, and then the random components. But what is effectively going on is that we are calculating each of these different slopes and relationship across each of the clusters, so across each of these schools or countries or regions or whatever the cluster is. And these will all have the same slope. So these lines are all parallel. And actually, sorry, this should be one per, not individual, but it should be one per country or one per cluster. And then the intercept here will vary across all of these clusters. And therefore, we can calculate cluster-specific intercepts. And the variance sigma 2 u, it tells us how spread all of these lines are. So the bigger this variance, the more distance there is between all of these parallel lines compared to the overall black line that is the population average relationship. So when we have small sigma square u, this means that all of these lines are very close to each other and close to the overall mean. Whereas a high level of variance at the cluster level will suggest that there is a lot of spread across all of these parallel lines calculated in each of the clusters that we have, or in each of the country. But what this also means is that technically, so we can calculate the residuals for each of these countries. So we can calculate how much of a distance there is between, let's say, this red line and the overall black line, this yellow line and the overall black line, and so forth. So we can estimate this distance and therefore also see how the various countries fare compared to the overall level. So the closer this distance is, the more it means that that specific country has a value that is very close to the overall observed level in all of the sample. Whereas, of course, the farther away the values are, so on the cases here on the left and the right corner of this caterpillar plot, this is how this is called. This plot is called as caterpillar plot. So the more distant these are, the farther away the average, let's say, life satisfaction in Bulgaria would be from the one observed in all of the countries and in all of the European countries. And this one here would tell you that it's also quite distant, but in this case, it would be a much higher average life satisfaction in Denmark and a much lower average life satisfaction in Bulgaria compared to the overall life satisfaction observed across all of the European countries. All clear so far? So if there are no questions, let's assume that, that we have an example here so that we can also see what we obtain when we run these models and how we interpret these models. So in this case, we're going to go very simple. So we will just assume that we're interested in the relationship between two variables. So, actually, I can see here that I've written depression score here and material deprivation. So I apologize. This should be depressive scores. So let's assume that we have 27 countries and that we are interested in the relationship between happiness and depression. And we only have two levels. So we have individuals within countries. So in this case, what we are doing is that we are modeling the happiness observed for each individuals in each different country as dependent on their depression score. And in the model, we therefore allow for an overall average relationship plus or minus the depression score for that subject, which will depend on how far away that country is from the overall observed relationship, as well as how far away that subject is from the average observed in the specific country J. So we would split this relationship between the fixed part and the random part. And as you can see in Stata, this is usually done by using the mix command followed by the outcome variable, in this case, happiness. And then we would have here the various independent variables. And in this case, we only have one, that is depression score. And the way that we tell Stata that the data is multi-level with people nested in countries is by adding here these two parallel lines that say this is the way the data is clustered. So we have people are clustered within countries. So we're telling Stata there are two levels, and the higher level is country. So what Stata is going to give us is these outputs. So we will now go through the interpretation of these outputs and roughly see what we have observed and how we interpret all of this. So the first thing here, you can see that there are 27 countries, as I mentioned before. And once again, let me laser point it. So we have about 27 countries here with roughly 2,547 observations. And if you kind of divide this, on average, there are about 94 people per country, with a range, with some countries that have as little as 51 observations and others that have up to 150 observations. And then we have here two separate parts of the model. So we have the fixed part of the model, and then the random effects parameters. So how do we go on and interpret this? So let's start with the fixed part, because this is really the easy part of the model. And I say it's easy because we actually interpret this the same way you will interpret any output from a standard classical linear regression model. So the constant here would tell us that for respondents with no depression scores, so when depression is equal to 0, the average happiness score across all of the countries is 7.032. And the other fixed estimate that we have is the one of depression. So this would be our beta 1 slope, average slope. And this tells us what is the relationship between depression and happiness. And this tells us that as the depression scores increase by 1, on average, happiness levels are lower by a factor of 0.583. And you can see from the confidence intervals and the p-value that this is a strongly significant relationship, suggesting that when depression scores go up by 1 unit, we can expect happiness scores to reduce by somewhere in between 0.49 and 0.67, with an average lower score of 0.58. So this is the same interpretation of a standard regression model. What we additionally gain from the mixed models that account for the structure of the data are these two values here that are known as the random effect parameters. So the way you interpret this is that the first one, so the variance of the constant, is really the variance observed at the level 2 of your data. So in this case, at the country level. And it tells us how much variation there is across the countries. So you can see here that the variation is 0.4. It is significant, and it kind of ranges between 0.2 and 0.7. And a high value of this variation here suggests that there are quite a lot of differences in the average level of happiness across the different countries. And if you remember, if we kind of go back to the caterpillar, so this is what really that variance is telling us. So it's calculating the variance of all of these distances and tell us how much variation there is between the overall level and the level observed in each of the countries. So if you had a variable and a variance here with estimates very close to 0, that would suggest that these countries don't really differ too much on their average level of happiness. Whereas when we have higher values of the constants, of the variances of the level 2, this suggests that there are substantial differences across countries in the average happiness scores. And then you can also see here that the other value that the Stata give us, or any other packages give us, is the variance of the residuals. And this is the variability in the happiness at level 1. So this is the variability at the person-specific level that is still to be explained by the model. So that is still unexplained by the model. Although we have already accounted for depression, there is still quite a lot of variation at the individual level in their happiness scores. And given that happiness goes from 0 to 10, such big variance suggests that at individual level, not at country level, but at individual level, there are a lot of variations across individuals. And you can imagine that the scores go from 0 to 10, so there is variation within across individuals at level 1. And so far, just accounting for depression doesn't explain much of these residuals. And once you actually have calculated these, slopes and the random effects at the country level, we can also then go on and plot the slopes for each of the different countries. And as I said, for instance, in this case, this would be an example of how the slopes would look like. And I, once again, down here should have been depression. I apologize. I've updated the slides, and some of these things have, I haven't noticed. But you get the idea here that you can calculate the slope for each of the specific countries. And effectively, that value that we observed here, so the variance of the constant, is actually telling us how much variation there is in these slopes. So there is in these intercepts of each of the countries compared to the overall intercept and to the overall association. Compared to the overall slopes observed across all of the countries. So at the moment, I've just introduced the two-level model, and I've just looked at an example where we only have one covariate. But of course, this can be more complex. So first of all, we can have multiple covariates in the model. But also, technically, we could also have more levels in the models. So, we will look, I think, at just one example in Stata today on how to deal when you have, more than two levels, and also, how to calculate, for instance, the ICC when you have three level models. But once you get the idea and the basic principle and the reasons why we move from single level models to, for the reasons why we move from simple standard linear regression models to mixed or multi-level models that account for this structure, then once you have that, once you've understood this difference, all the rest is just a further complexity, but the principles would always remain the same. So with three levels, you will look, for instance, at the variance that is between the school and the overall level, and then also between the region, let's say, where the school is and the overall level. So if there are no questions so far, or no further questions, or any questions, no. So remember, that when we are dealing with multi-level models, there are still, assumptions that we need to check. But, obviously we have, like kind of almost scarcity, model misspecification, linearity. These are things that you should be checking for. But instead of having, independence of observation, like another, the assumption when we have multi-level models becomes that the observations are independent within each of the clusters. And in this case, we also assume that the residuals, so the level 2 residuals, should be normally distributed. And we will see some examples on how this is done in practice. But these are the kind of the replacement of the assumptions that we would have for a single level regression model. So is it worth it? Is it worth doing all of these extra steps when we have a nested model? And also, was it necessary to actually account for this structure of the data? So if we want to answer this question, one way to do it is to check and test with a likelihood ratio test whether accounting for the structure of the data is necessary. As I said before during the lecture, there might be cases where if you had a variance partition coefficient equal to 0, then effectively, the clustering and the level 2 groups don't really matter. So one way to do it is to look at the VPC and see if this is equal to 0, but that's a bit of a cumbersome way to check it. The most common way is to use the likelihood ratio test that compares the kind of a likelihood or that checks how the fitting of the data is with a certain model, and then compares these two likelihoods to see whether we should be rejecting or not the null hypothesis that the simple model is better than the nested model. So we usually do it using, we can do it by hand, but obviously this is not always done, and we tend to just rely on the likelihood ratio test calculated by the statistical packages that we use. So if we had, the same model with happiness and depression, with and without the accounting of the structure of the data. So you can see here, that here we are just calculating a standard linear regression modeling where we don't tell Stata that these data are nested within country. Whereas in this case here, we actually further tell Stata that it has to account for the structure of the data and the fact that these observations are nested within country. So then, we can just run a likelihood ratio test, and this test will give us a p-value that tells us whether there is or not enough evidence against the simpler model. So it tells us, whether the evidence against the use of a simpler model is strong or not. So whenever you have, usually the assumption is that the simpler model is nested in the more complex model. So whenever you have a p-value that is less than 0.05, we would suggest that we would conclude that there is strong evidence against the simpler model. And therefore, we should be encouraged to use the model that does account for the structure of the data, and therefore does account for the level 2 country in this case. account for this structure of the data, what usually happens is that we would have much smaller standard errors, and therefore, the associations and the p-values would look much more stronger than they would be when we consider the structure of the data. And also, we've introduced today, this concept of partitioning of the variance when we have different structure. And this is how we can handle the fact that the data are not independent of each other, but that they only are independent of each other within a certain cluster. And we also introduced this initial idea of a random intercept model, where we account and we allow for an exploratory variable to be introduced in the model. And we allow, therefore, the slope of the relationship between x and y to vary across different clusters and different countries.
Thank you for watching. For more information, visit our website www.radiance.org.uk.